All right, here we are, section 6.2, energy, heat, and work. What we need to define in any sort of system is we need to define, or any sort of problem, we need to define the system and the surroundings. It's important to be able to define where the energy is coming from and where it is going. The source of the energy, such as a container with chemical reactants and products, is known as your system. The rest of it, well, surroundings. So the universe is comprised of a system and its surroundings. Now, there are different types of systems. There are open, closed, and isolated systems. Examples: an open system would be a fireplace burning wood. A closed system would be a pressure cooker. Compare a closed system to an isolated system. Well, an isolated system would be something like a thermos. Now, the comparison there is that pressure cooker, well, if you put your hands on that, that's still going to be hot. That's still producing heat and exuding heat. Whereas a thermos, it's insulated. It's keeping that closed system, well, contained even further. Now, here are kind of some visual representations of it. We've got our Erlenmeyer flask without a cap. We've got our closed system, so an Erlenmeyer flask with a cap, and then we've got our isolated system, where an Erlenmeyer flask has a cap and has an insulated layer surrounding it. Now, work in heat flow. Work, or W, is the energy resulting from a force acting on an object over a distance. Okay, so I do work whenever I push something. The flow of energy that causes a temperature change in an object or its surroundings is known as heat, also denoted as Q. Both work and heat can be exchanged between the system and its surroundings. Now, workflow between a system and its surroundings, work done on the system, your W is going to be greater than 0, so it's positive. An example of that, and what I would recommend before you really get comfortable of, less than 0 or more than 0, is to think about an example. W is positive when a system is a car and a person is pushing that car. So if the system is a car, an example is a person pushing that car. In that case, W is positive. If the system is a car, an example is a moving car hitting a person. Okay, so that is an instance where W is, well, less than 0. So W is negative. Work is done by that system compared to work being done on that system. The key here is your system is the car. Okay, so either that car is doing something to the outside or something from the outside is being done to that car. So the workflow between the system and its surroundings. This right here, we've got our surroundings indicated in blue, and then we've got our, I guess that's like a manila envelope colored system. In this case, work is being done onto that system, hence W is greater than 0. The opposite, W is less than 0 when work is being done on the surroundings from that system. Heat flow between system and its surroundings. When heat is added to the system, Q is positive. So an example of this is heat is transferred from a person's hand to an ice cube. So if you've got an ice cube in your hand and you basically close your hand off on that, heat is going to be transferred from this hand to the ice cube. Now that seems a little bit weird because, well, if you're holding an ice cube in your hand's going to get colder. Well, it's getting colder because the heat from your hand is basically being transferred into that ice cube, causing it to melt. Okay, now heat is released by a system. Well, your Q is negative. In that case, well, an example is a bowl of cold water left in the freezer. Heat is going to be transferred from the bowl into the freezer as the water cools and then freezes. So whatever heat was in there is going to be transferred out of it. So that would be an example where Q is negative. Again, your heat transfer from the surroundings to the system, or from the system to the surroundings. Q is greater than or Q is less than. Now, determine whether the value of W or Q is positive or negative in each of the following scenarios. If a person rolls a bowling ball across the floor where where the bowling ball is defined as the system, in that case, what you have is W is positive. Okay, so that work is being done on that system. B, a person rolls a bowling ball across the floor where the person is defined as the system. In that case, W is negative. Finally, an ice pack is placed on a person's sore back where the ice pack is defined as the system. In that case, Q, or heat, is positive. The first law of thermodynamics basically states that energy can move between a system and its surroundings. Some types of energy can be converted from one form to another. The law of conservation of energy states that energy cannot be created or destroyed. Okay, sort of like the law of conservation of mass. It can just be transferred from one form to another. The first law of thermodynamics states that the energy of the universe is constant. So that kind of goes hand in hand with that conservation of energy. The internal energy of a system is defined as the sum of all kinetic and potential energies of the particles within that system. So the internal energy is taking into consideration all the particles that are in motion, those with kinetic energy or with higher kinetic energy, and those that are, well, not in motion, those that have nothing but potential energy. This includes the motions of the molecules inside that system. Excuse me. This also includes motions of all the atoms and subatomic particles within the molecules. Absolute values of U are difficult to actually determine because of the vastness of it all there. Okay. Now, what about changes in internal energy, delta U? Changes in internal energy, delta U, are more commonly measured by comparing the final energy and the initial energy. When U final is greater than U initial, the internal energy of the system has increased and delta U is positive. Okay? When U final, so the internal energy of the final state is less than that of the initial, the internal energy of the system has decreased and delta U is negative. What we always do to look at this is we compare the work and the heat by looking at delta U is equal to Q plus W. Now, another way that you can look at all of this information and look at this whole concept is, well, Q as positive or negative. Does the system gain or lose heat? If it gains heat, positive. If it loses heat, negative. W, work is done on the system or is work done by the system? On it is positive. By it is negative. The system gains internal energy or loses internal energy. If it gains, it's positive for delta U. If it loses, it's negative for delta U. So, in effect, here's kind of what we're looking at here. So changes in work or heat affect the internal energy of the system. Q equals 400 kilojoules, W equals negative 90 kilojoules. So we've got, well, heat coming into the system from the surroundings, work being done by the system onto the surroundings. What's the net there? Well, the net, or delta U, is going to be an overall positive 310. Now, if we have heat leaving the system going to the surroundings and work leaving the system going to the surroundings, then we have a delta U of negative 490 kilojoules. Now, a good way to kind of visualize these sorts of exercises is to look at this. What we've got here is a reaction occurring in a flask that releases 890 joules of heat to the surroundings, and the gas produced performs 450 joules of work on the surroundings by pushing a piston upward. So here's our piston. Now, if you're at all thinking about vehicles, well, this is a good visual for an internal combustion engine. So we've got these reactants here. And what they're going to do is they're going to release heat, and then we're going to see this gas emerge here, and it's going to cause this piston to go from this position to this position right here. Okay. Now, what we need to ask ourselves, is this a closed, open, or an isolated system? Now, this is a little bit tricky because on one hand, you could look at it and say, well, it's closed because we got the cap there, but we've also got this piston here. So this would be considered an open system. And the reason for that is you do have some relief almost from the pressure that would accumulate here. Okay, determine the signs of Q and W for the system. Okay, so our heat, and we're given this information, it releases 890 joules of heat. Our Q is going to be less than 0, and our W, we're performing work, 450 joules of work, our W is going to be also less than 0. Now determine the delta U for this overall reaction. Okay, so what we would do is we'd look at this and we'd say delta U is equal to negative 890 joules plus negative 450 joules. And that's going to equal a grand total of negative 1340 joules. All right, everybody. To see some more application of this, or we're going to see some more applications of this in a little bit less abstract way. So right now, these are just your concepts. Understanding the concepts, whether heat is being released or absorbed, work is being done on the system or by a system. All right, well, we'll continue on.